For years, safety standards focused on the physical machine. If a wire snapped or a sensor shattered, the system had to handle the failure safely. But autonomous driving introduces a different threat. A system's hardware can execute flawlessly, yet still cause a crash because it fails to understand the environment, like a camera overwhelmed by morning glare. SOTIF Clause 9 acts as the safety argumentation, a rigorous architectural blueprint of proof designed to address this crisis. It replaces simple compliance checklists with a logical structure for proving a system's competence. Proving absolute mathematical perfection across every possible driving scenario is impossible. Instead, Clause 9 requires engineers to demonstrate that any remaining flaws, the residual risk, set at or below a level that society deems acceptable. This shift marks the transition from mechanical reliability to cognitive competence. Engineers must now provide rigorous proof that the software can accurately comprehend a chaotic physical reality. To evaluate an autonomous mind, we first have to take the infinite, unpredictable risks of the open road and organize them into actionable categories. First, there is Area 2, the known unsafe. These are the flaws we've already identified, like that camera blinded by the sun. Engineers design a fix and then use a strict empirical process called verification to prove that the specific repair actually works in the real world. But the greater threat lies in Area 3, the unknown unsafe. These are the edge cases and environmental anomalies no engineering team has even imagined. To tackle this, Clause 9 mandates validation. This exploratory mission forces the system into extreme scenarios to drag hidden risks into the light where they can be identified, reclassified, and corrected. Building a safe vehicle requires looking past the flaws we can see on a test track and actively hunting down the invisible dangers waiting just beyond the edges of our current imagination. However, engineers cannot simply put a car on the road and drive random miles forever, hoping they eventually stumble into every possible Area 3 anomaly. Instead, the industry relies on the Pegasus 6-layer model. This framework deconstructs the sheer chaos of the physical world into organized, testable variables. The model categorizes the driving environment from the ground up. Layer 1 defines the physical road geometry. Layer 4 introduces dynamic objects like unpredictable pedestrians, and Layer 6 tracks invisible digital data like V2X communication signals. By combining different parameters across these 6 layers, engineers generate highly targeted simulations. They create a dense, interlocking net that sweeps across billions of potential scenario combinations. Mathematically structuring the environment allows engineers to replace blind guessing with a deliberate dragnet that captures the unknown. Even with mountains of data from structured scenarios, one question remains: how much testing is truly enough to prove the vehicle is safe? SOTIF Clause 9 establishes absolute mathematical limits, starting with the acceptable harm rate, a macro-level societal goal. This goal is logically fractured into formulas calculating variables like hazard exposure or uncontrollability. The result is the rate of hazardous behavior, a hyper-specific target for individual components. For example, to meet the top-level safety goal, an engineer might calculate that a specific camera's perception algorithm must prove it will trigger a phantom braking event less than once every 10,000 hours of driving. Achieving this level of statistical confidence provides an ironclad defense of the vehicle's engineering, grounding the entire safety case in hard data. Ultimately, SOTIF Clause 9 applies rigorous logic to the infinite unpredictability of the open road, providing the mathematical evidence required to conclude that a system is safe for public use.